Hello everyone, and welcome to today's webinar, Understanding and Troubleshooting Kubernetes Connectivity Issues. So in this presentation today, we'll show you how to identify, understand, and solve the most common Kubernetes connectivity issues. So before I introduce and hand things over to our speaker, Karthik Prabhakar, KP, we have a few housekeeping items to cover on this presentation and the webinar platform. So first off, today's webinar will be available on demand after the live session and will be accessible through the same link that you're using now. It should take about 15 to 20 minutes for that presentation to be live. Copies of today's slides can be made available. You just have to email contact@tigera.io to request your copy. And most importantly, we would like questions about anything our speaker is presenting. Please feel free to ask them through the Ask a Question interface in the BrightTalk application, and we will take questions as they come if we can, but we also will reserve time at the end of this webinar for a full Q&A session. So without further ado, I am pleased to introduce today's speaker, who is first time. I've been doing this now for something close to 30 webinars here at Tigera. This is the first time I've had the pleasure of having Karthik, otherwise known as KP, join us. So welcome, Karthik. Karthik is the Senior Director of the Solution Architecture at Tigera. And you can see there everything he's done around secure application connectivity and helping customers. So without further ado, let's get into the presentation. So Karthik.
Thanks, Michael, and good morning or good afternoon or evening, depending on who everyone is. Looks like we have actually a pretty massive audience here, so glad to see all of you join. Obviously, when you look at Kubernetes and the sort of different frameworks for Kubernetes, for connectivity that Kubernetes presents, there are abstractions that are used, and they're used for different reasons, right? So there's obviously things like making sure that your pods, which are your atomic unit of work in Kubernetes, can communicate with each other. So we'll spend a little bit of time on that today. And because your pods are dynamic and transient, Kubernetes presents this abstraction called services, right? Where you have a nice abstraction in front of dynamic and transient pods. And we'll explore that as well. And how you find services is by leveraging constructs like DNS. But then beyond that, once you get past the basic connectivity, how do you secure your workloads so that only the right workloads are allowed to talk to each other? You have the right level of isolation. That is afforded by network policy. Ingress is a construct that is commonly used for traffic coming into the cluster, especially if you're looking for layer 7 termination and host headers. And that's also something that's commonly used in Kubernetes deployments. And increasingly, over the last couple of years, 2 or 3 years, you actually find that a lot of microservices deployments in Kubernetes benefit from deploying a service mesh like Istio together with Kubernetes because of the value it provides in observability, traffic management, security, and so on. So all of these are sort of constructs that you get with Kubernetes, and so it's no surprise that a lot of people are intimidated by looking at all of these constructs and trying to understand, and certainly when they have issues, troubleshoot it. And the way I look at this is, when you look at a formal dinner setting, you look at all of the different choices available to you in terms of your silverware, right? Do you really need 4 forks? Do you need 5 knives? Do you need 2 spoons? And you could sort of look at that in Kubernetes as well. Do you really need all of these abstractions? And the way I tend to describe it is each of these abstractions, each of the place settings is there for a specific reason. You don't need to use all of them. You could probably get by just using a fork and perhaps a knife. But if someone places a soup bowl in front of you, you're going to have a hard time using a fork to slurp up your soup. So that's the similar way that I tend to look at Kubernetes connectivity abstractions, in that you don't necessarily need to use all of these abstractions. Some of these might be sufficient, like going with basic pod and service connectivity and perhaps network policy. But ultimately, as you start to deploy real-world applications, it's best to understand where each of these abstractions is the best fit so that you can pick the right tool for the job. And so given that we will not have time to cover all of these in sufficient depth in this webinar today, I'm going to split this up into multiple sessions, and today we'll focus on the core elements of pod connectivity using CNI, We'll also talk about services and KUBE-PROXY, both using the newer IPVS-based KUBE-PROXY as well as the IP cables-based KUBE-PROXY, and also how DNS and service discovery works in a Kubernetes context. And then in a subsequent webinar, we'll cover topics like network policy, ingress and ingress gateways, as well as service mesh and greater depth. That way we can spend sufficient depth on each of these topics. So that said, I'm going to make do just a quick intro about Tigera in case you haven't heard of Tigera. Tigera has been involved in Kubernetes since the early days and has been very focused on the networking and network security within Kubernetes. Obviously, we've also been working upstream, and in fact, some of the upstream concepts or the core concepts of Kubernetes like network policy, how CNI is used. Tigera has had a direct hand in enabling some of these concepts and in many cases even maintenance, such as in the case of CNI. We've also been very involved with service mesh technologies like SVO and Envoy. And today, when you look at a number of the very large Kubernetes deployments, the most advanced clusters, generally you find Calico widely deployed as part of that, Calico being Tigera's flagship project. Now, skipping past the introductions here, for this particular webinar, I'm going to make some assumptions on your profile. I'm going to assume that all of you on the webinar here have some basic Kubernetes awareness, if not in-depth awareness on the connectivity side, at least being able to understand concepts like kubectl and the API server and the concept of a pod. I'm going to assume you already know that. And I'm assuming that means you've already used kubectl and you've already used some of the basic kubectl commands like kubectl get pods, describe pods, get service, kubectl logs, and so on. And we'll walk through that as well. I'm going to assume familiarity with Linux, including basic connectivity tools like ping and traceroute, which we'll obviously use in troubleshooting, being able to do lookups using dig and NSLOOKUP, being able to do IP route show to look at the Linux routing table, and just basic understanding of Linux connectivity. How does connectivity work through Linux? We are specifically focusing on Linux. Tigera also provides connectivity via CNI, Calico CNI, as well as policy in Windows as well, but we're not going to cover Windows in this particular webinar. Now, the intent today is we'll take a quick run through CNI and pod connectivity, how that works. We will use Calico as an example, using Calico CNI and Calico networking. Concepts presented here would be a little bit different with other CNI plugins, and we can certainly cover some of those in future webinars as well. Then we'll take a quick look at a live cluster and look at how we can troubleshoot basic pod connectivity issues. Then we'll switch back and look at services in Kubernetes and KUBE-PROXY, the basic concepts there. And then again, having covered that, we'll switch back to a live cluster and show how end-to-end connectivity works, including DNS as well, right? So with that said, let's jump into CNI. So the basic concept in Kubernetes is, in a typical worker node, you have a kubelet that is running as part of your Kubernetes cluster. In effect, the kubelet is responsible for launching pods once the pods have been scheduled on a given worker node. And a pod ultimately is a set of containers that are serving an application with a common network namespace associated with them. So once a pod has been scheduled on a given worker node, the kubelet is responsible for launching that pod. And specifically, to get that pod connected to the network, the kubelet will call out to the CNI plugin. The CNI plugin is typically stored as a binary on the host with the configuration normally stored under /etc CNI net.d. And what happens is when the kubelet launches the CNI plugin, together with the IPAM, the IP address management that goes hand in hand with the CNI plugin, in effect, it's the job of the CNI plugin to assign an IP address, or the IPAM plugin to assign an IP address to that running pod, and essentially take that virtual Ethernet connecting that pod to the host that the kubelet has set up, and make sure that the connectivity works for that pod to the rest of the cluster and to all of the other pods in the cluster. So in a nutshell, what happens in the Calico CNI case is that the kubelet calls out to the Calico CNI plugin and either the host local or the Calico IPAM module. And when it's asked to network this particular pod, it finds a way to assign an IP address to the pod and then gets that pod connected to the network. The way it does that is obviously when you have a virtual Ethernet that connects the pod into the host networking namespace, in effect, an IP address gets assigned by Calico IPAM, and it writes that workload ID to the data store, which happens to be either Kubernetes or it could be a standalone key value store like etcd. And in effect, what happens then is that now we need to get that pod connected to the rest of the network so that it can communicate with pods running on other worker nodes. And in effect, what happens in that scenario is that Calico CNI, in effect, creates the workload ID in the data store. And separately, we have another Calico node agent, which is running as a daemon set. So that is a pod that gets automatically started on every worker node in the cluster as the worker node bootstraps. And the Calico node agent has something called Felix, where Felix realizes, look, I have a new pod in my node, and I need to create a little route in the Linux routing table that says to reach this particular pod. In this case, the pod's IP address is 1.2.3.4. I want to send traffic down the virtual Ethernet assigned to the pod so that local connectivity within the node works. Separately, if you have, depending on the connectivity mode chosen in Calico, Calico gives you a variety of modes. We have agents running on all of the other nodes as well. And if you happen to be using VXLAN, where you're using VXLAN for encapsulation between nodes, in effect, the Felix nodes, the Felix agents and other nodes, in effect, also discover the fact that this workload happens to be running on worker node 1. And the Felix agent in worker node 2 essentially creates an aggregate route pointing to the pod IP, or in fact, an aggregate route pointing to a range of pod IPs. The next hop for that being the worker node 1 and pointing to a VXLAN that Calico device that Calico creates in the Linux kernel. And ultimately, traffic that is sent to that particular device gets encapsulated in VXLANs, i.e. Ethernet packets encapsulated in UDP, in IP packets with UDP port 4789 and sent across the wire. So in effect, what happens is all of the other nodes in the cluster now know how to reach this particular pod that has been bootstrapped. Calico does support other modes of operation as well. Another common encap mode that's used, a simpler layer 3 encapsulation rather than encapping at layer 2, which leads to less overhead, is something called IP and IP, which is simply encapping IP packets in other IP packets. So the packets coming in from the pod are encapped into a bigger IP packet, but in this case using the source and destination IP of the hosts themselves. So all of this traffic flows seamlessly across any intermediate infrastructure as long as you have IP connectivity between hosts. And essentially we have an internal protocol that we use. Specifically, we use BGP using a daemon called Bird to communicate routes between different nodes. And in effect, when traffic gets sent by the pod, they are encapped into these bigger packets and sent across the wire using IP and IP encapsulation. And each of the addresses there, 1.2.3.4, 5.6.7.8, are all just IPs given to pods. These are all derived from a cluster CIDR that is used when you deploy the Kubernetes cluster, and ultimately are mapped into a pod CIDR, which is used by Calico IPAM to assign IP addresses. Calico also has a more sophisticated and advanced capability of being able to not use encapsulation at all and simply use normal IP addresses with no encapsulation. And in this case, if your worker nodes are all in layer 2 adjacent in the same layer 2 segment, perhaps in a similar availability zone within your cloud environment, or in the same subnet within your on-premise environment, or if you're able to peer Calico with your infrastructure, for example, you can peer your Calico node agents with things like your top of rack and be able to share your pod IPs as first-class IPs within your infrastructure. In this case, we'll notice that the route actually points to dev eth0. rather than previously pointing to dev VXLAN.Calico or dev tunnel 0. In this case, what you're doing is we're simply using the Linux kernel for normal IP routing. We're in packets on the wire. And in this case, obviously, you have to make sure that your intermediate firewalls, things like your security groups or NSGs, do not have additional restrictions on traffic between pods, because in this case, we're just using the pod IP to send the packet out over the wire. And this makes troubleshooting a lot simpler, but obviously you do need to make sure that your network infrastructure is able to carry the pod traffic from host to host. So those are your basic concepts and the different modes that Calico can work in, right? And when you deploy Calico as part of your Kubernetes cluster, you pick the manifest and you customize the manifest to specify the mode that you want to use for traffic between nodes. So let's now take a quick look at how this actually works in practice. And before I do that, one other point I'll mention before I get to that is ultimately in Kubernetes, you assume that when pods come up, pods are given an IP address. Every pod has a unique IP, and there is seamless connectivity between pods. Now, in practice, you may not want all pods to talk to each other, and for that purpose, Kubernetes provides an abstraction called network policy. The Calico team actually helped define network policy upstream in Kubernetes. And fundamentally, you define your isolation primitives in a declarative manner, a little bit decoupled from your network connectivity. And ultimately, it's the role of a network policy implementation, which Calico also provides, to be able to dynamically segment your applications from each other as these pods come and go. And for this purpose, essentially what Calico does is leverage the Calico node agent to create this declarative policy, but instantiate it using whatever mechanism, whether it's IP tables and IP sets, or XDP at a lower layer in the Linux kernel stack, to be able to dynamically create rules for isolation at the point in which the pod connects into the host. So you're already isolating the pod even before it connects to the host. And optionally, Calico can also do this policy-driven protection for the host interfaces as well, to not just protect pods, but also to protect services in Kubernetes, such as node ports, as well as other host networked applications, as well as protecting the Kubernetes control plane itself. But that is a topic for a different webinar. So for now, let's go look at pod connectivity and how do we troubleshoot them. So given this flow of traffic between pod to pod, if you look at pod sending traffic to the host routing traffic to a remote host, ultimately, there are different places where things can break. First of all, the pod might show up and it might not get an IP address. So how do you troubleshoot that? Typically, you would want to look at the CNI plugin concern in the IPAM module, and the way you would do that is by looking at the kubelet logs, because the kubelet is what is calling these binaries. Second, is the pod sending traffic to the right IP address, right? If you're trying to reach another pod's IP over the network, is the pod sending traffic over the virtual Ethernet, and is it getting to the host? If it's getting to the host, does the host have the right routes to be able to route traffic to the remote host to get to the other pod? In other words, is the routing table correct? The fourth thing you will look at is, assuming the routing table is correct, has the traffic been encapsulated correctly? Or if it hasn't been encapsulated, is it still being sent out over the wire or the virtual wire? Is it going out over the Ethernet interface? The fifth place you will look at is, if it's being sent out over the wire, is it being received on the remote node? In other words, has your network infrastructure in the middle actually carried the traffic all the way over to the remote node? Do you have a security group or NSG that is preventing traffic? Do you have an intermediate firewall? Is your intermediate router dropping traffic? So if the traffic actually gets to the remote node, that's a good sign. So traffic has actually made it all the way to the destination node. And at that point, is it actually being routed? So does the destination node have the right set of routes, and is it sending it to the destination pod? So that's ultimately the last step you would look at. And if that works, then guess what? For the return traffic back from the destination pod back to the source, you would essentially retrace the steps, but in the opposite direction. So let's do this. Let's go take a look at a live cluster to see how pod connectivity works before we get to the services topic. So what I have here is a cluster with a couple of worker nodes and a master node. So if I do a kubectl get pods all namespec. So I have a cluster with 3 nodes, and if I do a kubectl get pods all namespaces, essentially you see I have Calico running in my Kubernetes cluster providing connectivity. I have DNS being fulfilled by CoreDNS, and I have KUBE-PROXY, standard upstream Kubernetes KUBE-PROXY, providing the services connectivity, right? So that's what's running in that cluster. A couple of worker nodes, so I can go look at these worker nodes as well. But if I want to do things like watch my kubelet logs and my worker nodes to see pod IPs being assigned, I would look at the kubelet logs, and that is typically observed using journal-ctl. So essentially you would do a journal-ctl-fxe. These are the various kubelet logs which are running on that particular node. So now let's do something interesting. Let's go launch a couple of applications. So I'll do a I'm just going to deploy an Nginx application together with the CentOS pod as a client. And in effect, I've created a CentOS pod as a client, and I've created a couple of replicas of Nginx within the NS1 open namespace and a service that is fronting them. So you'll notice that I have the CentOS pod that is running, that's gotten an IP address from the pod CIDR range to the 10.23 range as my pod CIDR, and a couple of Nginx replicas which are part of a deployment and fronted by a service called open-nginx. So now if I go back and look at where these pods have been scheduled, if I looked at my kubelet logs on this particular node where some of these pods got scheduled, you'll notice that Calico provides some detailed information in the logs in terms of the IP address assignment, the fact that these pods are getting connected. So if the pod shows up and it doesn't get an IP address, that is the first place that you would look to see what happened. Why did the pod not get an IP address? And typically, it would lead to something like a potential configuration error in your Calico manifest where you haven't configured it correctly. But and where you would want to look for that is under CNI net.b. And what you should see there is the different configurations which Calico automatically sets up as a daemon set. So this is all automatically set up by a Calico manifest when you deploy a cluster. So in effect, the configuration for what you're deploying is stored here. And typically all of this is seamlessly configured by Calico, including the access to things like kubeconfig and so on. Now, the next thing you'll want to check is, in this case, since my pod came up and an IP address was assigned correctly, now how do I reach other pods in the network? So let's do this. So let's do a kubectl exec into the pod. So we're going into the pod which is running in NS1 open namespace, and the pod name is CentOS open. Right, so now we're inside the pod's namespace, and now we have to figure out, can we connect to other pods? So let's say we're trying to connect to the CoreDNS pod. That is the IP address of the CoreDNS pod. So can we ping it? Guess what? We're able to ping it. So that's great, because now we're able to connect from this CentOS pod to other pods within the infrastructure. And the way this actually works is ultimately based on Linux doing the routing from the pod network namespace using the standard Linux routing table and being able to route to other nodes. So let's look at what that looks like. In this case, in this particular cluster, I've deployed it using VXLAN. So if I look at my cluster, essentially what I have is I have Kali interfaces. If I do an IP address show, essentially I have the Ethernet interface, which is ENS5 in my case. The Docker bridge is unused by Calico, so we ignore that. And what we have, and ignore the IPVS Kube IPVS, that's for services, we'll come to that in a second. But for every pod that is running on that particular node, Calico creates a Kali interface. So since I have 3 pods on this host, I have Kali interfaces for each of them. And in addition, I have a VXLAN interface that's set up for encapping via VXLAN, because I deployed the cluster using VXLAN. So if I go look at a particular host, if I do an IP route show, in effect, what Calico has set up is it set up a /32 route for every pod running on that particular host, pointing to the particular Kali interface. Similarly, Calico, the Felix agent, is also set up an aggregate route, as you see here, for traffic destined to pods on remote hosts, so a /26 route, pointing to the host that pod happens to be running on. In this case, it points to that remote VXLAN endpoint on that host and says, send it out the particular device, VXLAN Calico, so that the kernel actually does the VXLAN encapping. Often you want to make sure that things like your MTU are correct. This is also things that you can tweak via your Calico manifest. Most of these are typically set at defaults, which are pretty safe. But generally speaking, that's all there is to it in terms of making sure that your pod connectivity between hosts works correctly. It is simply to make sure that you have the /32 routes for the individual pods, and that pods on remote hosts, you have a route in the Linux routing table pointing to the corresponding hosts, right? So if those do not exist, what do you do? Then you can actually go back and look at a couple of things. You can look at, first of all, what are my logs for my Calico node? Are there issues? Did I have issues in the Calico CNI plugin? And if the routes don't exist, I can go look at the logs for my Calico node pod to see if there's any errors there. So what I would do in that case is do a kubectl log. And in effect, if there's any errors in creating routes, or if there's any errors in connecting pods to each other, you will see error logs rather than info logs that Calico node says, oh, I'm having a problem connecting this pod. It might be a warning as well. So those are the things you want to watch out for. And you can see here, generally when things work well, you get informational logs, but things are very good because now you have pod connectivity between the CentOS pod and other pods in your infrastructure. So let's do one more thing. Let me go look at a different cluster where I have Calico deployed with straight IP without VXLAN encapsulation and look at what the routing table looks like here. So if I do the same thing here, I have, let me launch the same application. And what you'll see is the app starts up here with the same services and so on. And if I go look at the routing table here, on this particular cluster, notice that I have now the same /32 routes, which are added by /26 routes, but in this case, it is pointing directly to the ENS interface rather than pointing to a VXLAN interface. So in this case, Calico is sharing the routes with each other using the bird daemon, the same aggregate routes, but in this case, it is pointing directly to the destination host's IP address and pointing directly to the Ethernet interface without encapsulation. So the packets are actually being routed by Linux with no encapsulation. So now, if you're using Calico with no encapsulation, there is no packets and packets to troubleshoot. You're simply troubleshooting the pod IP packets all the way from source to destination. It also means that if you have things like security groups or intermediate firewalls, they are allowing the protocols and traffic that you want to allow between nodes. So you need to have the right holes in your external firewalls if you have those. All right, so let's come back to sort of the next set of troubleshooting steps. So we talked to making sure the pods have an IP. We talked about once the pods have an IP, checking to see that the pods are able to talk to other pods, whether they are pod network with a pod CIDR range, or whether they are host network. In my case, my hosts happen to have the 172.24.20 range, and that connectivity works between any set of pods, right? Assuming you don't have policy defined. Now, so far, everything is good in our scenario, and pods are able to talk to each other. So now, what is the next scenario we need to consider? And for that, I'm going to come back and stop sharing and go back to the slides here. So as we know, in Kubernetes, pods are dynamic and transient. So pods come and go, and for that purpose, pods are great to make sure that ultimately connectivity between pods work, because that's ultimately the unit of communication. But that's not sufficient, because if a pod dies, your application should not be affected. And for that purpose, Kubernetes provides an abstraction called services. And you define a service in a typical declarative fashion in Kubernetes using a manifest. And when you declare it, you use a selector that ties that service to a particular deployment. So in this particular example, the selector app equals my app will allow the service to be backed by any deployment that has that same selector, i.e. app equals my app. And ultimately what the service is saying is that I want the service port to be port 80, but I want you to map to port 9376 on the pod, which is the target port that I'm using. And ultimately what happens here is that when a pod is sending traffic to a service, the service assigns a virtual IP. In this example, I'm using 172.16.0.5 as a consistent virtual IP or cluster IP that fronts the service. The service itself is backed by these very dynamic and transient pods. And each pod, as you saw in my previous example, has a dynamic IP. In my example, it was a 10 dot address, 10.23. But in this particular example, the pod has a 192.168. And as pods come and go, the role of a service is to keep track of all of the individual pod endpoints, but dynamically map the 172.16.0.5 service IP or the cluster IP to one of these backend pods. And ultimately, when a different application like pod B tries to reach a service cluster IP, this mapping is dynamically maintained so that the application connectivity works even if one of the pods happens to die behind the scenes. And this function in Kubernetes is performed by KUBE-PROXY. So KUBE-PROXY, in effect, what it does is it watches the service in Kubernetes and watches the state of endpoints. And in effect, as a service determines through liveness and readiness checks whether a given endpoint pod is alive or dead. So Kubernetes has this concept of liveness checks and readiness checks, where it is constantly checking based on what you've configured in your application manifest as how you determine whether a pod is alive or dead. Service also dynamically watches that state, and ultimately KUBE-PROXY is watching the service and dynamically creates NAT rules in either IP tables or IPVS to manage that mapping between the service IP and the actual pod IP. So in effect, for a cluster IP, in effect, KUBE-PROXY is dynamically creating these IP tables rules. So that's how you get this mapping from the 172.16.0.5 to one of the pod IPs. KUBE-PROXY, there's a second mode called node ports, which in effect, because a cluster virtual IP is not typically accessible from outside the nodes themselves, if you're trying to access your Kubernetes service from outside the cluster, Kubernetes assigns a dynamic port typically in the range of 30,000 to 32. KUBE-PROXY also then creates rules for any traffic coming into the host from outside on one of those ports that Kubernetes has assigned to be dynamically natted into one of the pod IPs. And if the pod happens to be on a remote node from which the external traffic is coming in, KUBE-PROXY will also automatically SNAT the traffic so that the return traffic also egresses the same way. Fundamentally, what the function of a service is to provide a well-defined connectivity abstraction in front of pods, because ultimately pods themselves are dynamic and transient. So in Kubernetes, there's 4 different service types in common use. So I'll ignore none for now because that's not very commonly used. The default in Kubernetes when you create a service is to use something called as a cluster IP. In effect, what happens is Kubernetes assigns a IP from a particular range called the service CIDR range. Keep in mind the service CIDR range needs to be distinct and different from the pod or cluster CIDR range, which is used for pods. And in effect, as a service gets created, the Kubernetes will assign one IP address from that service CIDR range for that particular service. and that particular IP is called the cluster IP. KUBE-PROXY notices this and dynamically will create the rules in IP tables or IPVS. The more widely deployed implementation of KUBE-PROXY uses IP tables, but there's also a newer implementation that uses IPVS, and we'll actually explore both. The other type of service is, like I said, a node port when you need to access the service from outside the cluster. And yet another type of service is something called as a load balancer. And in this case, Kubernetes supports a number of well-known cloud load balancers, where in addition to creating the cluster IP, Kubernetes also assigns an external IP and can also talk to one of these cloud load balancers to be able to dynamically create the load balancing rules on this external load balancer so that those external load balancers send traffic to the appropriate node, where the KUBE-PROXY and the node plumbs in the correct external IP addresses and then NATing from that as well. So let's go take a look at how this works. Actually, before we get to dig into KUBE-PROXY, like Kube-DNS is ultimately how you would do a service lookup in Kubernetes, how you would discover services. The way this works is when you bootstrap the cluster, normally you have an implementation that's providing DNS in your cluster. In the current versions of Kubernetes, that happens to be CoreDNS, which is the implementation for KubeDNS. So in this case, what you have is a handful of pods. In my example, I'm showing 2 pods, which are running the CoreDNS application, providing the DNS server functionality. And they are backed by a particular service IP. In this case, I've assigned it the IP address 10.96.0.10, right? So ultimately, these multiple KubeDNS/CoreDNS pods are backed by a well-defined service IP. So anyone in the cluster that does a lookup at this particular service IP will get a DNS resolution of what they're looking for. The second thing that happens in Kubernetes from a DNS perspective is as pods come up, within the etc resolve.conf inside the pod, Kubernetes automatically sets up the correct values for the right name server to use. So in this example, the name server is given the service IP for KubeDNS, which is 10.96.0.10. And also it sets up the correct search path to use. So if you notice, the search path now includes the particular namespace that this pod is running on, service.cluster.local, followed by service.cluster.local, followed by cluster.local. So when an application in the pod does a lookup of a service name without giving it a fully qualified service name, in effect, KubeDNS first suffixes that service name with the fully qualified domain name for that particular namespace, .service.cluster.local, and sends that request to CoreDNS. And so CoreDNS is actually able to find the correct service IP for that particular namespace and the service within that namespace. Secondly, if that particular service is on a remote namespace, then ultimately that search path can help find the service on the remote namespace. By default, you're always looking up the local namespace first. And fundamentally, what happens with CoreDNS and KubeDNS is the resolution gets set up such that as services get created, the IP address for the service or the cluster IP or other service discovery artifacts can be discovered using DNS. DNS doesn't have to be the only way you do service discovery, but it is also a very common way that people use the service discovery in Kubernetes. So let's go take a look at my cluster again to see how this actually works in practice. All right, so coming back to my cluster here, where in this particular case, I have my CentOS pod, which is a simple client pod which I'm using, but I have 2 Nginx pods, which are both being fronted by a service. So if I do a kubectl get service -n ns1-open, notice I have a service called Open Nginx that I've created mapped to these 2 pods. It happens to be a node port, so it's got a port in that particular range, in this case 30,080. But also there is a cluster IP that's assigned. And notice that the cluster IP range 10.101 comes from a 10.96.0.0 range, which is completely distinct from the 10.23 pod range. So you have to make sure that your pod CIDR range and your service CIDR range are completely distinct. So pod CIDR and cluster CIDR both are used for the pods, versus the service CIDR is what is used for the services. And then the service CIDR range happens to be the 10.96.0.0/14 range, which is where this address gets assigned from. Now, let's look at the service connectivity again. First of all, in this particular cluster, I'm using the IPVS KUBE-PROXY for the KUBE-PROXY implementation. And so if I do an IPVS ADM-LN, and I also want statistics, notice that what I have here is IPVS is telling me that, look, here's my IP address and ports. So in this case, the service IP that's been assigned, or this case, it's a node port, traffic port 30,080. Similarly, if I look at the specific cluster CIDR that's been assigned, 10.101.204, you will find the particular service site. There it is. So you find the 10.101.204, and it gets mapped dynamically to one of the pods which are backing that service. And ultimately, I get statistics for input and output. But because this is being used for load balancing among the different pods, using a variety of IPVS load balancing algorithms. In my case, I've just set up round robin. Ultimately, traffic from individual clients are load balanced among the different destination pods. But what IPVS does is it sets up NAT using the net filter mechanism in Linux to be able to NAT that service IP pods backing it. So on the wire, when you see a pod reaching out to a service IP destination, what you'll ultimately see is the source IP address being the client pod's IP, and the destination IP on the wire will be one of the destination pod IPs. You will not see the destination service IP on the wire. And ultimately, the traffic goes from pod to pod. So you're following the existing steps I already described for troubleshooting pod connectivity. So now if I do a kubectl exec into my CentOS pod, and I try to do a few things. First of all, I'm going to do a curl on the service name. So it is open.nginx. Or was nginx open? I forget. The service name was OpenNginx, sorry. OpenNginx. And if I do that, guess what? It worked. I'm able to connect to Nginx. So what happened there? First of all, I did a curl with the service name. The fact that I used the name and not an IP address tells me that DNS is working. How did it work? Let's do a cat etc resolve.conf within the pod. What you see here is the name server's cluster IP is actually used as a target. So in other words, my pod has tried to talk to the cluster IP of the DNS name server. That cluster IP gets mapped to one of the CoreDNS pod IPs. So that mapping already worked. And then beyond that, that result came through. So CoreDNS was actually able to correctly resolve the IP and send the actual IP. So if I do a dig, I don't know if I have dig installed. You wouldn't normally install these inside a pod, but I'm just doing it for the sake of showing you how this works. Okay, actually, let me see if I should use the better client pod to troubleshoot. The fact that DNS lookups did work. So if you actually look at the DNS response that you get when you look up OpenNginx in suffix it by this particular namespace.service.cluster.local, the response back from the KUBE-DNS, i.e. CoreDNS, is to give you the service IP that is being assigned to that particular service. In this case, it would be the particular service IP for the OpenNginx service, which is the 10.96. whatever, sorry, 10.101.204.227. And then the next step was when I did a curl, ultimately that is what gets looked up. And then this particular pod, the CentOS pod, sends traffic to the 10.204 address, which gets mapped into the pod IP of one of the Nginx pods. In this example, it would be one of these. And then you would see the traffic flow on the wire with the source of the CentOS pod and with the destination of this particular pod. And if you want to trace and troubleshoot if that connectivity doesn't work, ultimately you're going back to pod IP connectivity troubleshooting, which is by doing things like IP route show, making sure that the routes exist. So in this case, since my destination is 10.23.186.196, this is the particular route that will be used. So that's how you would do connectivity troubleshooting for cluster IPs. In this case, if I was reaching out to the node port, ultimately in the node port case, you're sending traffic to the host IP. And in this case, since the destination is this particular host, the traffic will be destined to that particular IP address, but port 30,080. And ultimately, KUBE-PROXY simply sets up the rules in IPVS. Now, one caveat to that is that KUBE-PROXY's IPVS implementation still uses IP tables for things like node ports, and there are specific reasons for that. So if I do an IP tables save -key nat and pipe it to less, notice that there are still some routes that are being created by KUBE-PROXY for things like node ports. And specifically, these are to allow Kubernetes to use the best facilities available in the Linux kernel for a given function. IPVS is great for load balancing. It is not great for things like SNAT. So that's one reason why you'll find that KUBE-PROXY still uses IP tables for SNAT for things like node ports. But at the same time, the IPVS implementation always leads to a fixed set of rules independent of a number of services. So it still has some really good scalability characteristics, even as you get to many tens of thousands of services. Now that is the IPVS implementation of KUBE-PROXY. Let's look at now the IP tables implementation of KUBE-PROXY, which is an alternate implementation which I have running in my other cluster. In this case, the way KUBE-PROXY sets up rules is using the NAT table in IP table. So if I do an IP table save, let me make this bigger. -d nat, and if I pipe it to less, notice that in this case, KUBE-PROXY has created a number of rules. So the first thing it does is KUBE-PROXY will first set up a jump on the output chain to talk to Kube services. And within Kube services, if you look at what this does, for every service that is running in your cluster, it creates a set of rules saying point to a particular other chain called Kube service chain. And sets up also the masquerade rules when masquerading is required. So as an example, notice that for the service that I just created, which is the Nginx open service, I have these two rules, which says, here's setting up my masquerading rules and the jumps, and also I am going to do a jump to this particular Kube service chain. And so ultimately for every service in my cluster, including for the Kube-DNS service, including for the services that users create, like the one I created for Nginx Open, you'll find those two rules and then a jump. And then if you follow that jump, in this case for the Nginx Open, the jump is to, let's say, Kube service, this particular chain. So if I go look for that particular chain, which is right here, notice I have two rules as well. What that first rule is saying is I'm going to do this load balancing using a random with a probability of 50%. And for 50% of the cases, I'm going to jump to this Kube SEP with this IDE, which is randomly generated. And for the remaining 50% of the cases, I'm going to jump to this other chain called the Kube SEP with a different ID. And if I go look at what those two chains are saying, ultimately XAD. So here's the second chain. What this is saying is for 50% of traffic, I'm sending traffic to this one pod that is backing the service. And for the remaining 50% of time, I am sending traffic to this other pod, which is backing the other service. So this is how KUBE-PROXY does very, very rudimentary load balancing by using a Prabhakar. And ultimately, your traffic simply flows eventually to a pod, right? So if you're troubleshooting KUBE-PROXY, for example, if you're trying to reach a particular service IP and you're not able to reach the service IP, what you'll be doing is going through the sequence of 1, 2, 3, and 4 jumps for every service to see, hey, is traffic reaching that particular pod? A good way to troubleshoot that in practice, and I'll just give you this as a tip here, is you can use commands like watch -d, IP tables, ENL, -d on the NAT table, of course, which is where KUBE-PROXY puts its rules, and I'm going to grep with additional lines. Actually, let me do one thing here. I need the chain name. Let's say I'm troubleshooting this particular chain. The chain name happens to be this one right here. So I do a watch -d. Grep with 2 lines. Oops, I forgot. There we go. There's a typo there. And in effect, as packets come and go into the service, you will see this value change. So if I remove this value and just show you the entire thing without the grep, let me do this. So in effect, you will see the values change as packets come and go into the individual chain. Let me actually remove the grep altogether so you see how this will view in a typical environment. And as packets change, you'll see the packet counts increment. And because I've done a difference on the watch command, you see where packets are coming in. So you're able to go back and troubleshoot exactly which chains are hitting packets and which are not. And there's ways that you can do this in production at scale that we'll come back and walk through in the next webinar when we talk about things like policy and being able to analyze and understand things like flow logs as well. But now, at the raw level, you're also able to get the statistics using just raw IP tables. Or if you're doing the IPVS KUBE-PROXY, you can do this using the IPVS ADM with the stats. And similarly, use the watch command to see where the packets are coming in, which chains are hitting it. And if you're not able to get to a destination service IP, i.e. the NAT is not working correctly, then you can go back and troubleshoot the corresponding chains on that particular IPVS or IP tables rule. So let's come back to summarizing troubleshooting here. My browser just came back. All right, so now what we've seen is ultimately when you have to troubleshoot service connectivity, what are the different places you can look at this? First of all, are the pods that are backing a given service healthy? In other words, if you have a service that is being backed by 3 pods, Kubernetes is constantly doing liveness and readiness checks based on the liveness and readiness checks that have been defined by the application in the manifest to make sure that the pods are healthy. If the pods are not healthy, Kubernetes will kill them and try and restart them. But for whatever reason, sometimes the application fails, or there might be other factors where the pods cannot be restarted. Maybe you run out of capacity. Maybe you don't have enough memory or CPU for Kubernetes to restart the pods. So it's possible that none of the pods in your service are healthy. The way you determine that is if you do a kubectl get service and kubectl describe pod, see if the pods and the service are healthy. If they are healthy and the service IP is still valid, then the next thing you can check is KUBE-PROXY working correctly? And the way you would do that is by looking at the KUBE-PROXY logs to see if it is correctly plumbed the rules for the service. And part of that is also making sure that it is being able to correctly write to IP tables or IPVS to create the correct rules. And again, those should be logged using the KUBE-PROXY logs if it is unable to create the rules in IPVS or IP tables. And ultimately, the fourth thing you will check is your IP cables and IPVS working correctly? So in other words, when a destination or when a source pod is trying to reach their destination service, that those NAT rules are happening correctly. And for that, ultimately, what you're doing is you're keeping track of IP cables using techniques like tracing in IP cables, or you are using, in the case of IPVS, you're also keeping track of IPVS logs, which are also both IPVS and IP cables also log to the kernel logs, so you can actually log this and get some errors in the kernel if either of them have errors. So just wrapping up here, other things you can have, there's a number of tools. What I showed you so far is how you can do this imperatively, where you are going into doing a kubectl exec, you are pinging, you are trace routing, you are actually logging into a host and doing an IP route show, you're doing a TCP dump, you're doing a Wireshark. There are tools that make this much more, make this much more effective in actually practice in production at scale. And specifically dealing with this involves how do you as a cluster operator make this much more much more declarative, where end users can troubleshoot connectivity problems before it happens. The command, which are utility images or ksniff integrates with kubectl to make the snooping much easier. Also for Calico-related problems, we also recommend the Calico command. Things like Calico node status and other tools like that will show you when there's connectivity issues. So I also recommend using Calico. Last thing I'll mention is if you want to do this as a cluster operator and make this sort of troubleshooting information much more evident to users at scale, also come talk to Tigera, because we do have other products like Tigera Secure that are much more focused at operators to help operators be able to troubleshoot this at scale in production and provide the right level of visualization tools and visibility to be able to give flow information out to end users. So with that said, I am going to stop, and in the 4 minutes left, take any questions we have. Also, if you have any questions, or if you do want to follow up, do reach out to us either via the Tigera.io website or email us at contact@tigera.io, and we'd be happy to take any follow-up questions that way as well.
So if you guys have any questions, please ask them quickly. Unfortunately, the webinar is going to auto shut off in 3 minutes. So if this webinar does shut down, that's why. That's something we can't change once the webinar has started. So 3 minutes for questions. Otherwise, as Karthik said, we'll take questions on our website or by email. Or Yep. And also, as you mentioned, there will be another session of this covering the other topics, and we can certainly review some of this as well.
Yep. Now the questions that have come up on the chat, there's a question here saying, if we have two pods with running on the same node, will they talk over a VXLAN tunnel or over just raw IP? Ultimately, if you have pods on the same node, ultimately you're using the Linux kernel for the routing, and since you have routes in the Linux kernel that have /32 routes for each pod, ultimately everything in Calico is a routed hop. Everything, even from pod to pod on the same host, will still go through the underlying host, but it's not going to be encapped across VXLAN, because keep in mind, these are running on the same host. You have /32 routes for the source and the destination pod, and it's still a routed hop. It's still in Calico's network policy, but it doesn't necessarily be encapped into VXLAN, because ultimately VXLAN is being used for encapping in between nodes. Hopefully that answers your question. Happy to folks have questions. If not, we will wrap up.
We've only got a minute left, so I think at this point, I'd like to thank you guys all for attending. This webinar is great information. Thank you so much, KP, for presenting. And do check back. This presentation will be made live, and we can have copies of it sent to you if you'd like. And again, we do 2 a month. The next webinar is yet to be scheduled, but it will be in this month at the end of September. So look for notice on that. All for attending, and I hope you guys have a great day. Thank you.
Have questions? If folks have questions, if not, we will.
We've only got a minute left, so I think at this point, I'd like to thank you guys all for attending. This webinar is great information. Thank you so much, KP, for presenting. And you know, do check back. This presentation will be made live, and we can have copies of it sent to you if you'd like. And well, again, we do 2 a month. The next webinar is yet to be scheduled, but it will be in this month at the end of September. So look for notice on that. All for attending, and hope you guys have a great day. Thank you.